Hi class, welcome again to another session on biomaterials. So we have been discussing the topics in our second unit. So far we have discussed the stainless steel alloys and we have discussed the cobalt chromium alloys. So let us move on to the titanium based alloys now. So titanium has been used as a biomaterial for a very long time, since early 1930s it has been used as a biomaterial. So it is lightweight or it has got really low specific gravity and has good mechanical strength, chemical properties. When I say mechanochemical properties, it means that it can withstand quite a lot of load and it is inert. It doesn't react to body fluids and therefore it is like a perfect choice for making implants. Now, there are certain drawbacks of using titanium, which we will discuss towards the end of this session. But let us first of all see what are the good things about using titanium. For medical purposes or for some making surgical implants, there are four grades of pure titanium that are used and a titanium alloy that has also been used. The pure titanium is considered to be between grade 1, grade 2, grade 3, and grade 4. And the alloy is 6 elements of titanium, 4 elements of aluminium, and 1 vanadium. So Ti6Al4V is the alloy. So you can see that there are trace elements of nitrogen, carbon, hydrogen, iron, and oxygen. And the percentage of all these five elements is varying from grade 1 to grade 4. The nitrogen varies from 0.03 to 0.05% from grade 1 to grade 4. Carbon remains constant 0.1. Hydrogen also remains constant 0.015, and then iron varies from zero point 0.2 to zero point 0.5. Oxygen varies from 0.18 to 0.40. Now this is for grade 1 to grade 4. We can see that the Ti6Al4V alloy has got 0.05% nitrogen, 0.08% of carbon, then hydrogen is 0.0125, then you have iron of 0.25, and then oxygen is 0.13%. So grade 1 to grade 4, except for these five trace elements, the rest is titanium. So 98 to 99% is titanium. Whereas in this alloy, the last one, Ti6Al4V, other than these trace elements, you have 6% of aluminium and 4% of vanadium as well. The remaining percentage is of titanium. Now, titanium has got two phases. It has got an alpha phase and beta phase, and this is especially seen in the pure titanium. So, alpha phase is if titanium is treated in temperatures below 882 degrees centigrade, then it exhibits hexagonal pack structure when you visualize it through electron microscope, and that is called as the alpha phase titanium. Whereas if you heat it above 882 degrees centigrade, then the internal structure of the metal becomes face-centered cubic, and that is when the titanium is said to be in its beta phase. So both alpha and beta phase are present in your Ti4Al6V. This alloy has got both alpha and beta phase, and it has the same fatigue strength as the cobalt chromium alloys. Now, titanium is inert and does not cause any allergic reactions when it comes to the body. When it comes in contact with the body, again, it has low specific gravity, good corrosion resistance, and biocompatibility, and therefore it is one of the ideal choices for making medical implants. Now, titanium has got this property of formation of a stable titanium oxide on the surface of the metal. So now, one of the major advantage of this titanium oxide layer is that it is repairable. So for example, for some arbitrary reason, if the titanium oxide layer has been worn out or it is scratched, then it reforms, it reheals itself and then covers the entire metal. So this is one of the most notable features of using titanium based alloys is that the titanium oxide layer that forms on the surface is repairable. It reheals. So this gives it superior corrosion resistance when compared to stainless steel and other alloys. Now, like I said, when the oxidized film is scratched or damaged, it can reform, and therefore the corrosion resistance property of the material is maintained. Now, if you have, why do you add aluminium to Ti4Al6V? It is to stabilize the alpha phase, and vanadium stabilizes the beta phase. So the stabilization of these two phases gives it superior strength. So the structure can be strengthened even further through aging rather than annealing. So instead of annealing the metal to improve the strength, if you just let it age, if you just let it rest for a few days, for some specified duration of time, then it just starts to it strengthens further. However, vanadium has been proven to be toxic to the human body. Like if for some arbitrary reason vanadium starts to leach out of your titanium alloy, then that can cause cytotoxicity. That is, it can be toxic to the cells around it, and it causes harm to the body. So therefore, people have come up with titanium alloys that are without vanadium. So let us see a few alloys. So you can see, like instead of vanadium, people like alloys with niobium, zirconium, molybdenum, and tantalum, as well as iron, have been used along with titanium to form titanium-based alloys that are good biocompatibility and suitable for biomedical applications. So one of the major disadvantages of using titanium alloy for biomedical application is its poor wear resistance, right? And it is difficult to fabricate basically. So when I say poor wear resistance, it is like not very prudent to use it for making joint heads, because high friction and wear properties results in persistent deformation of the oxidative layer. So ultimately the thickness of your material is going to reduce because it is wearing out and new oxidative layer is forming. So it is ultimately the thickness of the material is going to get compromised. Also, if it is a joint that is not bearing much load, right, you can still use titanium for that, because even if the oxidative layer is exposed, so low shear stress would give adequate time for the implant to heal itself to form the oxidative layer again. However, if it is a load bearing joint that is like exposed to high shear stress, then cold welding starts to happen. That is, the implant is repeatedly exposed. Repeatedly the oxidative layer is getting disturbed, and that would accelerate the wear of the implant. So these are the major disadvantages of using titanium alloy. However, there are applications where titanium is very widely used, and one of the very popular use of titanium alloy is to form the outer casing of a pacemaker. The hermetically sealed casing of a pacemaker is often made up of titanium alloy. I hope you had a fruitful session learning about titanium based alloys along with me. I shall see you again with another video. Till then, take care.